All right, our next speaker is Maria Gorinova. She is currently a machine learning research engineer at Twitter. She's done a lot of work, including during her PhD her doctoral work on probabilistic programming, including the design of the Slickstan language, but also program analysis of probabilistic programs, including, for example, conditional independence by typing, or automated reparameterization, which we were just talking about. And she's going to talk today about program analysis of probabilistic programs. Welcome, Maria.
Thank you so much for the introduction. Hi, everyone. Thank you, Xavier and Jean-Baptiste, for inviting me. It's so nice to be here in person, giving a talk in person. Very excited. All right, so, well, that was me from the introduction. I recently finished my PhD in Edinburgh, where I wrote a thesis on program analysis for probabilistic programs. And today I will be talking mainly about this work, and hopefully towards the end, if there is time, I might mention some more applied probabilistic programming that we're doing at Twitter, well, or trying to. All right, so we already discussed today a little bit about what is probabilistic programming, like what it should be about, right? And in my mind, the ideal is that probabilistic programming should be about giving a domain expert the ability to write a model. They can write any model they want, and they don't have to think about inference at all. Magic happens, everything works amazing, and that's it, right? But we already heard today that this is not quite the case, and it's not quite the case because magic can't just happen. So I like to think about it this way. So in the ideal world, what we would want is to have a language that is user-friendly. So that includes automatic inference. We can write anything, and it's all automatic. It is general. We can express any model we like. And we have fast and reliable inference. However, what happens in practice, because this is such a hard problem, what happens in practice is that different languages sacrifice one or more of those things in some way. And here are some examples. So we have often approximate inference instead of exact, or if we have some sort of, if we have a very general language, then we need to use a general purpose inference, which might not be very efficient. If we are to have a very efficient language that is user-friendly, then we need to sacrifice some of its generality, make it, for example, like it was already mentioned that Stan doesn't allow directly the usage of discrete variables, and I'll talk about this more actually. So even though what we want is this kind of magic triangle with all these things on it, what happens in practice is that we are in a classic pick two scenario, or sometimes even pick one. And so what my PhD was about was really thinking about how can we take a language that maybe sacrifices one of those three things and use program analysis to make it better. And in particular, I will talk about one static analysis method that we did with Stan, and one dynamic analysis method that was implemented in Edward 2. Okay. Yeah, so that's the question. All right, so the first work I want to talk about is conditional independence by typing. That's a relatively recent paper. It was published in TOPLAS this year with my advisors Andy Gordon, Charles Sutton, and also Matisse Vakar. This research was all about Stan, which thankfully Joseph introduced just in the talk before, so I don't have to reintroduce much of this syntax. But basically what Stan is, in case you heard about it for the first time today, Stan is a quite popular probabilistic programming language. It's used a lot. It has very big community, very, very nice, very helpful community with more than 6,000 forum users. There are more than 5,000 citations of the main STAN paper. And there is also, I don't know if it's annual, I don't know, sometimes StanCon happens, and there are actually a lot of people, and it's great fun because you have these people from many different disciplines coming and saying things about their fantastic STAN models, and it's extremely interesting. And why is, I think the reason STAN is so successful, well, there are many reasons STAN is so successful, but if we look back at this triangle, in my opinion, it's most strong here, where user-friendly and automatic inference, and also great community. And here, because it uses a fast inference algorithm called, well, I'm going to mostly be talking about Hamiltonian Monte Carlo, but it has some pretty heavy restrictions on the kind of models you can specify. So you can't have unbounded recursion, for example, and you can't have direct encoding of discrete parameters. So what we wanted to do in this work is to address the problem with the discrete parameters. So firstly, why can't STAN have discrete parameters? Well, it's, as I mentioned, STAN uses Hamiltonian Monte Carlo. Hamiltonian Monte Carlo uses the gradient of the joint density defined by the model for efficiency. And that's the gradient with respect to the parameters theta. I'm not going to go into details of how this works, but you can kind of think about it as you have this, you can imagine your distribution that you would like to sample from as some sort of surface, and you push a pluck on that surface and give it some momentum, give it some kick, and then simulate the physical system of the pluck moving for a bit, and then stop it and take the end position as sort of the proposed sample. And this is where the gradient goes in this simulation. The problem with that is that because the gradient is taken with respect to the parameters, these parameters cannot be discrete because this gradient won't exist. So the trick is many people say, okay, you can't have discrete parameters in STAN, but that's actually not true. You can, but you have to do some work. So you need to manually marginalize them out in your program. And I'm going to give an example of what that means in a second. But the gist of this work was to take STAN with discrete parameters. So imagine that we can actually put in discrete parameters in that and do some program transformations, static program transformations, and get a regular STAN program that doesn't have discrete parameters. Now I say STAN, but I'm actually going to be giving examples with SlickSTAN, which is some previous work that essentially you can call it blockless STAN. Right? So this is STAN with these blocks. We already saw examples of the code, and SlickSTAN just doesn't have the blocks. So I will use them interchangeably. All right, so now to understand the problem, really, to understand how this marginalization works that allows us for discrete parameters, let's take this SlickSTAN program and imagine we want to have this discrete parameter. What does this program do? This is a change point model where we would like to model the rate of some disaster happening, but we think that there was certain year, so we kind of record the frequency of a disaster happening every year, and we think that there is 1 year where there was a change of this frequency, so it became more common, say. We don't know which year that is, so we have two rates here that are continuous parameters, and that's the early rate of disaster, the late rate of disaster, and we have some discrete variable, which is the year when the point changed happened, the change point happened. And then we model, this is the actual number of disasters. So you can imagine that this will probably be like 2020 and then suddenly this rate is way bigger or something like that, right? So we can't write this directly in slickstan or in stan because of this discrete parameter, but we can rewrite our program to marginalize it out. So what does this program correspond to? It corresponds to, this encodes this joint density over here. So it's the joint density on the data y, the continuous parameter enl, and the discrete parameter d. And it's basically product of all these factors that we see in the program. And what we need to do in order to marginalize out d is literally sum out d over all the values it can possibly take, like this. So we take this is the joint that we started from, and we sum it over all possible values that they can take in this marginalization. How does that look as a program? You remember that target variable from the previous talk? So here it's expressed. This is not in logarithmic space. So in the previous talk we had pluses everywhere because it was all in log space for numeric stability. But here we just have normal products to correspond to this equation. So it's the same program. Now instead of these twiddles over here, we have some multiplying the products into this accumulator, and we do that so it's an array, and we do that for every possible value that D can take, and then we just sum over this array. So sum all these values. That's it. And there is only one other thing that needs to happen in order for us to actually get the same program that we were interested in, which is that, so this is the original program. We got this program that actually corresponds to this joint density that doesn't have D in it. And in order to also get D, we need to add this bit, so we take this array of variables, and if we actually sample a categorical variable based on this array, we get a sample back for D. And it turns out that this program here is semantically equivalent to this program there. Right, so, okay, that seems that would be a bit ugly, but it doesn't seem very tricky, right? We just put lots of sums and that's it. Yeah, but what happens if we have more than one discrete variables? So this starts becoming a problem. Why? Because if we have, say, n discrete variables, we will have n-dimensional array because we need to consider every combination of what these zn's can be, which means n-nested for loops for us. So that doesn't really scale, and it's pretty bad. However, it turns out that if we look at the program structure, and if there is some sort of program structure, we can exploit it in order to make this more efficient. This is an example with a hidden Markov model over here, just a vanilla hidden Markov model. What we can do is actually sum in a more smart way, where we only do 2 nested for loops at a time. We have to do it many times, well, n times, but it's two nested at any point. And how does that work? Well, there is a method called variable elimination, which basically tells us how to do that. So if we have, again, this hidden Markov model here, and so let's say we want to marginalize out Z1, what we do is we look at, maybe for 1 second I should take a step back and describe this graphical model in case people are not familiar with it. So this is called a factor graph, and it's a bipartite graph where the variables are, the round variables here, the round nodes are variables in our model, and the square nodes are factors. So when we look at this, right? Each of those expressions over here in this product will be a factor. That's the idea, and this allows us to kind of like look at the components that make up our joint function. So we want to marginalize out Z1. We look at the neighboring factors, so all the factors in the joint that Z1 participates in, and we merge them together. So here we multiplied them together. We removed Z1, we multiplied them together, and we summed out over all possible values that Z1 can take. We spoke with it. And now Z1 is marginalized out. And if we take this factor and multiply it with these other factors, we get basically a density where Z1 doesn't exist anymore. Well, it's marginalized out. And we can repeat this process afterwards for Z2 and so on. Right, so the key idea of this research on conditional independence was to use information flow analysis and type inference to analyze the program, analyze the conditional independencies, figure out how we can factorize the program this way, and then use program slicing to separate different bits. The way we did that is with a semi-lattice of levels. So here, every variable in our program has this type level, which is either L1, L2, or L3. And we want information to flow from low levels to high levels only, but not vice versa. So information can flow from L1 to L2 and from L1 and L3. But because this is a semi-lattice and there is no relation between L2 and L3, information can't flow there. And that's a bit abstract. So maybe a better way to think about it is visually. So if we imagine we took our whole program and we separated it into 3 chunks of variables, XL1, XL2, and XL3, and 3 bits of code associated with, well, pairs like that, then, well, this is basically what we want to do, and this semi-lattice enforces this kind of thing. So now if you look at that, if you look at that graphical model, what we can do is we can take XL2, and we can marginalize it out without thinking about XL3. So that's XL2 and XL3 are conditionally independent given XL1. Right, and what this does in terms of actually rewriting our program is if we have this over here is sort of an HMM again, so this 3-variable HMM, like a different version of it. And if we want to marginalize out Z1, we can now figure out where each bit of program that corresponds to Z1 is, and take all these bits and put them somewhere else and rewrite our program to actually marginalize out Z1, which here is done with this syntactic sugar elim, but that's details. Okay, so to recap, what we wanted is we had this joint distribution over the data y, the continuous variables e and l, and the discrete variable d. And we want to sample the continuous variables and the discrete variable from that joint. But we can't do that, at least if we are using a method that uses the gradient. So instead, we sample the continuous variables e and l from the marginal of e and l given y. And then, given these samples, we can actually sample the discrete parameters from this conditional distribution, if we need them. The message I kind of want to take across here is that this is only one particular a sort of instantiation of a type system that can do program analysis for probabilistic programs in particular. So while working on this work, we actually proved that the previous work, the original SlickStan paper, what it did is to factorize the program in this way. So let me explain this. We have a joint between data D and parameters theta. What the type system of the original SlickStan did was to kind of separate the parameters theta into theta 1 and theta 2, and divide the program, factorize the program into this conditional P of D theta 1 and this conditional P of theta 2 given D and theta 1. And this allows us now to, so this kind of corresponds to generated quantities instance. So this allows us to use HMC or something like that for this joint. And then given samples, given these theta 1 samples from here, use some other inference algorithm like just ancestral sampling, like in generated quantities instance, to use to do the rest. In this work, the conditional independence type system allowed us to factorize the program in a different way, in this way. So we have, again, parameters theta. We don't even have to, like the method is general, so they don't even have to be discrete. We just do it for discrete because that's what made sense. But it can be any parameters. We can factorize the program into conditional only on, a margin only on theta 1 and theta 2, and a margin only on theta 2 and theta 3, because we have this thing that theta 1 and theta 3 are conditionally independent given theta 2. And again, this allows us to now use one inference method for this and another one for this, see. And I think this relates nicely with all these ideas that have been discussed today, and hopefully I think Jan Willem and Vikash might be talking more about ideas such as programmable inference or some sort of more, let's say, less automatic probabilistic programming systems where you have more control over how you do inference. And I think this kind of relates nicely to it because maybe we can actually use program analysis to give us those components which we can then choose with our framework what to do with. Let's say, I want to run HMC here and I want to run, I don't know, backward sampling there or something of the sort. Okay, so that was the first bit of research I wanted to talk about. That was the static analysis. And the second part of this talk is about dynamic analysis. This work was done partially during an internship with Dave Moore and Matt Hoffman. And you can find the paper in ICML 2020. So here the idea is, we mentioned reparametrization in the previous talk. However, here I mean reparametrization in a slightly different way. So maybe forget about the unconstraining reparametrization for a second. We're not going to think about that. Here's the problem. We're hoping that we can just input any program into an inference algorithm and get a result. But that's, even if in theory the algorithm supports that kind of program, that's not what happens in practice. Why? Because imagine we have something like vanilla Metropolis Hastings or Gibbs sampling, say. And imagine that we have a joint distribution with density like this. If we try to sample from this, we'll be forced to make very, very small steps because of how these algorithms work, right? And because there is this correlation between the variables x and y here, strong correlation. So it will be quite inefficient. We'll have to be like very, very, very slow. And if we use something like HMC, it will actually work okay here because of using the gradient and stuff like that. However, it has its own pathological examples. For example, this is news funnel, and By the way, I forgot to say earlier, the previous research was totally inspired by the wonderful Stan manual, which is like a gold mine for ideas to run program analysis on. And weirdly, this also is. So the news funnel is mentioned, and this kind of reparametrization is mentioned in the Stan manual, and this was also partially inspired by it. So here, if we run HMC, what happens is, due to the geometry of this density, it's like very, very highly curved in this funnel over here. So if we run HMC, it will kind of sample well in this area over here, but it will have trouble going down this funnel. And actually half the probability mass is down over here. So this is pretty bad. What we can do, though, is we can take, this was the definition of news funnel. We can take this, and instead of sampling from this joint of x and y, we can sample from the joint of x tilde, y tilde, where x tilde and y tilde are defined like this. So we take y to be the the scaled version of y tilde, and we take x to be the scaled, again, given also on this sample y, a version of x tilde. So now what happens is that we can sample from this joint, which is just a spherical Gaussian, right? And this is like very easy to sample from. And then we can take the samples that we got from this and transform them based on this function to get samples in the original space of x and y. We call this parametrization centered parametrization, and this no-centered parametrization. And that's quite often used in practice. However, there is a problem, which is, you might be looking at this and being like, okay, well, then why don't we just use this everywhere, right? Why don't we just always sample from spherical Gaussian and then transform our samples with a function? Well, the thing is that it's easy here because we don't have any data, but when we have data, things don't look like that. And here is a small study of this. Consider this model. We have some data, y, coming from a Gaussian with mean mu and standard deviation sigma, and we give mu some hierarchical prior to. This is the non-centered version of the same thing. Basically, instead of sampling mu here from normal theta sigma mu, we sample epsilon from normal 0, 1, and then shift and scale in order to get to mu. If we take Q to be the ratio between the number of data points in our data and the standard deviation of the data, and we try to look at the posterior distribution. This is a very simple example, so you can actually derive the posterior distribution analytically. If we do that for different values of Q, we see the following thing. So we see that when Q is small, the centered density looks very, very thin, and it's quite ill-conditioned. So again, we remember that running Metropolis Hastings on this was not very good. While for small q, the non-centered parametrization has this kind of like nice spherical form. So it's very close to the prior, basically. But as q grows, we see that in the centered case, this is quite well conditioned because even though it's elongated like that, it's actually they're actually not correlated. There is little correlation there. But in the non-centered case, we see this quite ill-conditioned distribution again. So what does that mean? It means that we can't just magically reparameterize our models without looking at our data first. And this is why I kind of call this research dynamic analysis for probabilistic programs, because we are not just looking at the program here, we are also looking at the input. We are also looking at the data and doing this either as a pre-processing step or some sort of augmented inference. All right, and what is this? What we want is we want to take a model like this. So this is sort of like a version of Edward II syntax, I would say, maybe like a cleaned up version, which is in Python. So basically you can think of Python functions that kind of generate our data. This is the centered version. What we want is to look at each of those lines and somehow substitute it with the non-centered version for this model. So we want to create instead variables from standard, normal, and then shift and scale. All right, I will speed up slightly in the interest of time. We did this with effect handlers, which basically means that we literally there is a function that you can define that is the effect handler that says what happens when you see a random variable constructor. So you see a random variable constructor, and instead of constructing the random variable directly, you say, okay, construct a standard version of this, and then shift and scale. And what the more interesting bit here was, in order to kind of incorporate this decision between centered and non-centered, we needed to relax somehow this binary choice. So the way we relax it is with this different parameterization, where lambda is between 0 and 1, and sort of says how non-centered our model is. So when it's 0, you can see that it corresponds to non-centered parameterization, and when it's 1, corresponds to centered parameterization. Then we used variational inference, and I'm not going to go into details about this, but basically what we did is that we try to, while we are learning the variational posterior, we're also kind of squishing and deforming the distribution at the same time using this parameterization, continuous parameterization that we define in order to reach the conclusion that basically it should be spherical like this. All right, and now there are a few more minutes, right? Yeah, okay. In this case. So these two bits of research were part of my PhD, but now I'm at Twitter and work on a bit more applied things. So I wanted to actually share one of the projects I work on with you, as I thought it's a very interesting and very kind of, it might be an encouraging example of where probabilistic programming may be useful. So Birdwatch, the project is called Birdwatch, is all about decentralized content moderation. What does that mean? Basically, you've all seen, I mean, I suppose like you use at least some social media, maybe not Twitter, but maybe Facebook or Instagram or TikTok, but you've all seen how much misinformation and disinformation there is online. So there will be false claims, or there will be claims that may be not quite false, but might be misleading, maybe people misinterpret them, and so on. And this has been hard, as far as I understand, for social media companies to deal with. And one of the reasons why it's hard is because why should social media or any particular company or any institution or any government should say what misinformation is harmful and what's not, for example? It's very, very tricky. It's lots of gray areas there. So why not the community deciding this, the community reaching a consensus about whether something is misinforming or not? And this is what Birdwatch tries to do. The idea is, let's say there is an example of a tweet when somebody said that whales are not actually mammals, blah, 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 something like that, right? And what a Birdwatch user can do is they can go and they can write a note. And a note is a different thing to retweeting or replying or anything like that. It's a different functionality. You write this note and you say, well, whales are indeed mammals, giving some explanation, citing some reputable sources, right? Great. And now what? Well, somehow we need to rate these notes and decide what's good and what's not. And we want to do this in a way that it's not dependent on Twitter, right? Or in any social media. There shouldn't be one person who decides what's true. So people rate, bird watchers go and rate these notes and say, okay, is this good or bad, up-rate or down-rated? And then the algorithm that we are developing actually takes their ratings and decides, looks for some sort of consensus. And if there is consensus, the note is elevated to be seen by Twitter users. So this is a relatively new project, I think a year and a half. Has been going on for a year and a half. It's already live in the US for some users. So if you're a resident in the US, you can go and register and become a bird watcher. And also maybe if you're a Twitter user, maybe you're able to see those elevated to like be seen by the wider community notes. Here is a bit more about how it works, how it looks. So like a tweet, and then you see this little snippet, oops, that contains the note. Right, and then the note ranking. So this is the core bit of what we need to do is we need to take all the ratings and decide what notes are good and what are not. And this is the current algorithm. What it does is this is the score that somebody gave to a user U and a note N, and this is the score 0 or 1 that they gave to certain note. We model this as some intercept, just global intercept, and you have the user intercept, so how inclined the user is to upvote, then the note intercept, which really is the note helpfulness, and this thing, which sort of says, well, if the user's views align with the note, then they're more likely to operate that note. Currently, this is not modeled in a probabilistic way. It's just, we just train it as minimizing some least squares, essentially. But I'm working on models in NumPyro to help improve this. And that's it. I'll take any questions there might be.